Welcome to the Statics and Strength of Materials, Lecture 3. We'll be reviewing vectors today. What is a vector? Vector is a parameter that will possess magnitude and direction. And it will, examples of that will be displacements, velocities, accelerations. Here's an example of a vector. Vector P points from point A and is directed in a particular direction, has a magnitude as an example. A scalar, in the other hand, is a parameter that possesses a magnitude but does not have. You don't have to describe it with a direction. Examples of that is mass, volume, temperature, speed, even. Vectors can be classified as a fixed or bound vector. A fixed or bound vector is a well-defined point of application that cannot be changed without affecting an analysis. So you can move this vector around, and it doesn't really affect the analysis. A free vector can be freely moved in space without changing their effect on an analysis. So sliding vectors may be applied anywhere along the line of action without affecting an analysis. And equal vectors have the same magnitude and direction. Here's an example of two equal vectors that have the same direction and have the same magnitude. A negative vector is one where you have a given vector, but then you have a vector in the opposite direction. Both are directed in the opposite direction, and they have the same magnitude. Here's an example of a vector at a 30-degree angle, directed from point A. It is 10 pounds force. In this example, force is a vector. This vector has a direction and it has a magnitude. The experimental evidence shows that if you have two forces, such as two vectors P and Q, say they have a force applied on point A in the direction, in this direction, with that magnitude, and then you have another vector Q from point A directed in this manner with a magnitude of Q, that in fact, you can determine a single resultant force that represents the effect of these two forces, these two individual forces. This resultant is equivalent to the diagonal of this shape, which contains two forces in adjacent legs. So if I have a force P and a force Q, I can take this force Q, translate it upwards to this dashed line, and whatever that dashed line ends, that vector ends, which is this point, you can draw a line that's directed from point A to that point, and that resultant R can be determined. Once again, I can do that same thing with vector P. Vector B can be translated to the right where the dashed line is, and starting at the end of vector Q, I can draw that vector P going from this point to that point, and then draw a line that goes from point A to the end of vector P, which was translated, and that will now represent vector R, which is the resultant representing the effects of these two vectors, P and Q. So vector, in this case, forces are considered vector quantities. We can use the trapezoidal rule for vector addition. And so the idea there, you can use a triangle rule also. In this example, I have taken vector Q and moved it upwards, and you can see that in this figure. So the resultant is basically the addition of vector P and Q, and that's your resultant R. This is your resultant vector here that represents the effects of these two vectors. So I've translated Q upwards, the magnitude stays the same, the direction also stays the same, as you can see. In this figure B, what I've done, in this case, I have moved vector P to the right, translated that. I haven't changed the problem because the magnitude is the same and the direction is the same. So here I have that, and then when I connect points A and C, I get the resultant, which is P plus Q. So that's your vector addition there. If I wanted to determine through the law of cosines the magnitude of r, I can do so. If I know the angle between vector p and q in this example, that forms this angle right here, I could write that r squared, which is the magnitude of this vector right here, AC, is equal to the magnitude of p squared plus the magnitude of q squared minus twice the product of p and q and the cosine between these two vectors right here, these two lines, AB and then BC. I can also apply a law of sine. So sine of A divided by the magnitude of P is equal to the sine of B, this angle right here, divided by this resultant magnitude, equals the sine of C, this angle right here, divided by Q, this magnitude here. And so this relationship can be used. You can also realize that the vector addition is commutative. For example, here I have P plus Q, but here I have Q plus P, yet the resultant R is the same. You can also apply these addition of vectors through repeated application of the triangle rule. And so in this example, I have a vector P, Q, and S. I can add Q and S first to get this vector Q plus S, and then I can add P plus Q plus S to get this resultant vector P plus Q plus S. So repeated application of triangular rule is acceptable. The polygon rule is also acceptable. If I have P, Q, and S, I can just add them all three to get this resultant P plus Q plus S as your resultant vector. So the vector addition is associative. I can add P plus Q first, then I get this resultant vector here, add that one to S, and then I get this resultant vector. I can also add Q plus S first, such as the way I did it here, and then add it to P to get this total vector resultant. I can also multiply the vector P by a scalar quantity 1.5 as an example. It will make the magnitude of that vector larger, the direction the same. I can multiply by negative value and I get a vector directing the opposite direction, but it's in the general direction of that line. What are concurrent forces? That's another concept that will be accounted, that you'll encounter in statics. It's a set of forces which all pass through the same point. Here, vector S, P, and Q pass through point A. That's a concurrent set of forces. And so these forces can be applied to a single particle. And in fact, you could add them up to basically get a resultant force R. So for example, this vector Q is this one, this vector P is this one, this vector S is this one. And so when I take these three vectors and add them up, I get a vector that's a resultant goes from point A to this point. Vector force components do exist, meaning I can have a single vector of the same magnitude and direction. So this is one example. There's another example, and there's another example. And you can have two or more force vectors that have different magnitudes and different directions, and yet give you the same resultant force vector, single force vector. Let me move on to the vector product of two vectors. What is that? There's a concept of the moment of a force about a point. And so it's more easily understood through the application of a vector product or cross product. What is that exactly? So the vector product of two vectors P and Q is defined as a vector V which satisfies the following conditions. Here I have two vectors P and Q which define this plane and have an angle theta in between. The cross product of P and Q gives you a line of action V that's perpendicular to that plane that was formed by P and Q. The magnitude of this vector V can be calculated. It would be P times the magnitude of P, the magnitude of Q, times the sine of the angle between those two vectors. The direction of V can be found through the right-hand rule. For example, here you can use your hands with a thumb. And so if I put my hand on P and rotate it to get to Q, the thumb will point upwards. As a consequence, we know which way the vector is applied. The vector products are not commutative, meaning if I do Q cross P, I'll get the negative P cross Q. You can see that very clearly. If I put my hands along P and rotate it to get to Q, my thumb will point upwards. But if I now take my hand and put it on along vector Q and rotate it towards P, then my thumb will have to move downwards. They are distributive. So if I have a vector P and I have two vectors Q1 and Q2, I can calculate the uh, vector product by distributing P to each of these Qs. And you can see that here. They're not associative. In rectangular components, you can define three unit vectors. A unit vector is a vector that has unit magnitude. But here you have a vector I, J, and K, and they're aligned along each of the axes. I is aligned with X, J is aligned with Y, and you also have K aligned with Z. If I take the cross product of I and J, I with J, I will get K as the resultant vector that comes out of the cross product of I cross J. And that's this example here that you see here in the middle. If I take the cross product of I and I will get 0. If I take the cross product of J to I'll get the negative of the vector I got here, because if I put my hands along J and I rotate that to get to I, my thumb will be pointed in the opposite direction than the axis Z. In general, if I do the cross product of I and J, I'll get K. If I do the cross product of J and K, I'll get I. And if I do cross product of K and I'll get J. If I go in the opposite direction, I'll get the J cross I'll get negative K. K cross J, I'll get negative I, and so forth. You can calculate the vector products in terms of two rectangular coordinates. So say I have a vector P. Vector P has components Px, Py, and Pz. You can represent vector in those three axes, I, J, and K. So I have a value of Px along X. I have a value of Py along J, a value of Pz along this Z axis. So any vector can be represented along those three axes. If I also have vector Q, I can also produce the components of those. And if I take the cross product, the formula is simply this given here at the bottom. You can also calculate that. For example, if I want to find the first component that goes here, I'll draw a line downwards here across it, a line down here across it. So I get Py times Qz minus Qy times Pz. That's the determinant of these four values here at the bottom right. And that's exactly what you see written here, times I. And then you can perform the same calculations for the rest of them. For example, let's do this last one here is K. So I draw a line downwards, a line horizontally, and so then I have the determinant of these four values here, Px times Qj minus Py times Qx. And so that'll be that component right here. So that's a coefficient of K. And so now, as you can see here, you get a vector. And that vector, again, will be perpendicular to the plane defined by the vector P and the vector Q. And its magnitude can be found through the formula that was discussed earlier, which is this one right here. P, magnitude of P, magnitude of Q, and the sign between the two vectors. Let me look at why cross products can be very useful. They're used for moment calculations. For example, you have a force F and a distance D from this axis. You can calculate how much moment is being applied, for example, to this wrench in this case. So that'll be F cross D or D cross F. We'll see that later. Um, we can also use it for area calculations. If you have a vector A and a vector B, I can calculate this area by taking the cross product of A and B. You can also use it for a volume calculation, which involves a mixed triple product. In this case, the cross product of V and W give you that area, and the dot product of that with U, this vector U, and I'll define what a dot product is coming up, will give you the volume of this structure of this geometry. Let's discuss now what is a scalar product of two vectors. So if I have two vectors P and Q, the dot products of P and Q will be equal to PQ cosine theta. And it's useful because if you know the vector P and you know the vector Q and you know their magnitudes, you can actually determine from this information, you can determine the angle between them. So that's the usefulness of this approach here. Scalar products are commutative. So P dot Q is the same as Q dot P. Are distributed. You can distribute them. So P dot Q1 plus Q2, you can distribute P dot the vector P to each of these Qs. They're not associative. The scalar products with Cartesian unit components is basically P dot Q. So I have a vector P represented in each of the axes, so Px, Py, and Pz, dot product with Qx, Qy, and Qz, you can determine that this dot product is basically Px plus Qx plus Py times Qy plus Pz times Qz. And you can see that very easily because if I take Pxi times Qxi, I have to calculate I dot I, but I dot I is 1 because when I look here, the magnitude of I is 1. The magnitude of Q is 1 in this case. So this is 1. The cosine between the two vectors here, I and I, is 0. So cosine of 0 is 1. So all this is 1. So the dot product of I and I is 1. And so when you multiply P x times Qx, you get that. If you take the dot product of I with J, you will see that that will be 0. Because the magnitude of P is 1. The magnitude of Q is 1. The cosine between the two angles is 90 degrees. So that will be 1. And so the I dot J, the I vector and J vector, that will give you 0. And so forth. As you multiply everything, you will find that Px, Qx plus Py and Qy plus Pz, Qz is the dot product of P and Q. You can also take the dot product of the same vector P and P, and you will get Px squared plus Py squared plus Pz squared, which is the magnitude of P but squared. The angle between the two vectors follows that I can calculate that easily by isolating cosine theta. And so that's what you get. You can project a vector on a given axis, and that will become very useful. So say I have a vector P, and when I want to project that along line OL. So all I have to do is to take this P and multiply by the cosine theta to get the projection of that vector P on OL. And that's fairly easy to prove. You can check it out. Use the same concepts discussed earlier. And here you will find that this works out very nicely. For an axis defined by a unit vector, say you have a unit vector, and the unit vector lambda, in this case, is defined by the three angles theta y, theta z, and theta x. If lambda is a unit vector and it was defined by these angles, you can calculate how this vector p is projected along that unit vector lambda. And that calculation will end up being px cosine theta x plus py cosine theta y plus pz cosine theta z. I want to discuss very quickly what's the mixed triple product of three vectors. Very quickly is a cross product of P and Q and then dotted with S. That will give a scalar quantity. And that's one way to calculate volume of a geometry, as discussed earlier. Um, and you can form 6 different mixed triple products with S, P, and Q, which will have equal magnitudes but not the same sign. So you will have different signs, but they're all equal in value. Evaluating the mixed triple product will give you this quantity here. You can do it at home and just calculate the cross product of P and Q, and then take that and dot product with S. You will get this this calculation here, which is the same as taking this determinant. Again, that will give you the volume of the vector S, Q, and P. For example, I showed it here. So the 3 vectors here, you can calculate the volume of this geometry. Great. So now we're going to move on to rectangular components in space. And so, so here I have a vector F that goes from point O to point A. And this is defined by theta y and also this angle phi here. The theta y is the angle between OB and OA. Phi is defined between OC and the x-axis. So I can resolve this force F into the horizontal and vertical directions. And that's easy because that's, again, projecting F onto this line. And so the force F projected onto this line is the F times cosine theta y. And that's what you see here. Now, if I want to project F onto OC, I definitely have to just look at 90 minus the theta y, because this angle OA and OC, that angle is 90 minus theta y. So projecting F onto OC is F times cosine 90 minus theta y, but the cosine 90 minus theta y is really the sine of theta y. So that's why you see that I was able to resolve this vector F into these 2 vectors. Now what I want to do is resolve this vector F along the z and x axis. To do that, I can project it. I can project it again one more time. I can project FH, which is this one right here, and I get FH cosine P. That gives you this component. But I already know that FH is F sine theta from the previous calculation. So then Fx, this vector Fx, is basically F sine theta y cosine P. And then Fy is FH sine phi. So I'm able to resolve it in the manner. And then now I get F sine theta y sine phi. So this actually a slight error. So this Fz is what I meant. So I was able to take Fh and then resolve it into this vector. And so I apologize for this small error. This should be Fz. Okay. Now I have the ability to determine that. If I know the angles between F, the vector F, and the axes, so I have this vector F, and I know the angle between F and each of these axes, that makes it easy because all I have to do is resolve F vector onto each of the axes, and that's just projecting it. So the vector F projected into OD is just F cosine theta x. The vector F projected onto this, if I know that angle, which is theta y, I can now determine Fy, which is F cosine theta, and so forth. Fz is the same way. This vector F can be projected to this z-axis, and that'll be F cosine theta z. So the vector F, you can factor F in each of these, and you get this cosine theta x, I hat plus cosine theta y, j hat plus cosine theta z, k hat. I can factor that F, and I get lambda hat, which is the unit vector that describes the direction of that vector F. It turns out that cosine squared theta x, cosine theta y, cosine theta z, if you add them up, you get equal to 1. Has to be. So lambda is a unit vector along the line of action F, and cosine theta x and cosine theta y and cosine theta Z are known as the direction cosines for F hat. So let's look very quickly what happens if I know the coordinates of this point and the coordinates of this point. How will I define a vector that goes from this point to that point? Very quickly, I can determine that. Basically, take x2 minus x1. So that'll give you the component for dx, which is the components of the vector d hat that points from m to n. Y2 minus y1 gives you dy. And then z2 minus z1 gives you the components of dz, which make up this vector d hat. So given these 2 points, if I want to find the vector that goes along them, defined by vector d hat, I can find it simply by subtracting the coordinates of n and m. I can also determine its magnitude from here to here, and that's simply d. So the unit vector defining lambda hat is 1 over d dx I hat plus dy j hat plus dz k hat. If I have this, I have the unit vector. If I multiply f to each of this, I get the force resultant that will be acting on this along this line. So given the force along the points M and N, I'm able to determine its magnitude and direction properly. Let's hit a few examples. I'm going to go through several examples to explain this concept. So say you have 2 forces acting on a bolt at a point A. My question is, given a force P, 40 Newton, given a force Q, 60 Newton, given this angle of 20 degrees, given this angle 25 degrees, can you determine the resultant that's acting on this bolt A, this point A, which is where the bolt is? We can do it through graphical solution and trigonometry. So let's hit the graphic solution first. Well, I know P where P is and where Q is. So I can just use a parallelogram. I can just draw this P, a dashed line going upwards of the same direction, same magnitude as P. I can draw the same line here as Q, translated here, same magnitude, same direction. And where those 2 dashed lines meet, I put a point. So from point A to that point is vector R, and that's your resultant. You can do that with a ruler very quickly, and you can calculate the distance between this point and that point with a ruler. That will give you the magnitude of 98 newtons. And then you get the angle of 35 degrees, which can be determined quite quickly. So that would be the quick way of one way of doing it graphically. Another way that you could, there's many different ways to do this problem. We can use trigonometry as well. So the graphical solution is exactly what I explained. Move Q to this dash line, and then simply draw these points, this line, and then just measure it. And then alpha can be calculated with a compass or some other way. But you can quickly determine its magnitude and direction. Trigonometry can be used. We already discussed that there's 20 degrees per the problem statement. That's vector P. Vector Q, which was over here, had an angle of 25 degrees with respect to vector A and vector P. And you can see that here in the problem statement. This vector P and vector Q is rotated about vector P by 25 degrees. So all I've done is translated that vector Q from here to here, okay? And so now can use trigonometry. I know P, the magnitude of P is 40. I was given Q, the magnitude of Q is 60. I know the angle between this vector AB and BC using trigonometry, because this is 25, this has to be 155 because it has to add up to 180. So using that information, I get the resultant, 97.73. From the law of sines, I can take sine of A, this angle here, divided by this magnitude is equal to sine of B, which is this angle divided by this resultant. I can solve for sine of A, and so that I get Q sine of B Q divided by R. And then I know this B, which is 155. This angle here is 155. I know Q is 60. R is 97.73 from the previous problem. And so now I get an angle A of 15.04 degrees. So that's this angle right here between AB and AC. That's your angle right there. So therefore, if this is 20 degrees and that's 15.04 degrees, then the total angle is 35.04 degrees. And that's a resultant direction and magnitude. You can see that that matches very well what we got with the graphical solution. There's other ways to approach it. You can take this vector Q and just find its components in the X and Y directions. So X and Y directions by projecting it into the X and Y direction. You can take vector B and project it into X and Y directions. Add P and Q in that manner, P plus Q, and then calculate the magnitude of P plus Q, that vector, which is going to be exactly this vector R. And you will get 98 newtons and the angle of 35 degrees. Let's look at the problem of a barge, which is pulled by two tugboats. So you have this barge pulled by these, two tugboats, A and B, sorry, A and C, at a point B, and these at an angle 30 degrees in this manner, and then you have an angle alpha here. This tension in these ropes are gonna be basically a force acting along B and A and B and C. The question is that if I have these two tugboats, if the resultant of the forces exerted by a tugboat is 5,000-pound force directed along the axis of the barge, meaning it's directed along this axis, the question is determine the tension that's in each of these ropes to make that happen for an angle of 45 degrees. And the second question is what value of alpha will give you the lowest tension along BC? So we can use a graphical solution. We can use trigonometry. So very easily, we know the vector 5,000 is in this manner, right? We know this 45. We know this 30 degrees. We know this 45 degrees. It's given to us. So we can again use basically translate this vector here to get basically this length. So graphically, you can just draw this line here parallel to that one, and when you do that, you basically get the total resultant in that direction very, very quickly, and that'll give you the non-resultant direction. So given this information, given this resultant 5,000 pounds, you can determine this distance and this distance because you know their angles. You can also use trigonometry very quickly. Tension T1 divided by the tension rope 1 divided by sine of 45. So I have basically this magnitude divided by sine of 45 equals to tension 2, this magnitude 2 divided by sine of 30 is equal to the sine of the 5,000 divided by sine of 105. I know this ratio. I know this is 105 because it needs to be the summation of all the angles should add up to 180. I can now solve for T1 and T2 independently. So the trigonometry solution is pretty straightforward as well. I can now determine the minimum tension in rope 2 by being smart about it. So if this is my resultant of 5,000 pounds, I can look at for rope 2, I can kind of look at which one gives me the lowest distance that basically connect lines 1 and 1 prime. So this line here is the one from BA, And so I'm looking at which one gives me the shortest distance, and you can see it's the one that's perpendicular. Everything else will be longer. So that therefore this has to be perpendicular. So that's perpendicular. I know that's 30 degrees because of that angle there. So that's 30 degrees. So, and that's 90 degrees, has to be perpendicular for it to be the smallest vector. And so that forces alpha to be 60 to get the lowest tension in that row. Given that information, you can get the tensions in each of the row by projecting the vector 5,000 pounds into each of these. Okay. So very quickly, we have found the solution to example 2. I discussed this earlier quite a bit, but you can take any vector f and project it into fx and fy. You can resolve it into those components. And that's another way to approach any of these problems, and probably the easiest approach. Any vector can be represented along the rectangular components of a Cartesian system. And so this approach works very well. We refer fx and fy to be the scalar components of f hat, and it's one approach to resolving a lot of these problems. If I want to find the resultant force due to 3 or more concurrent forces, all I have to do is find the components of P along the X, Y, and Z axis, the components of Q along the X, Y, and Z axis, and S along the X, Y, and Z axis, add them up, and I'll get the resultant. That's the easiest way to solve these problems. And that's exactly what I've done here, showing you how to do that in a 2-dimensional way, but you can do that also in 3 dimensions. If I want to find the magnitude of R, all I have to do is to take, calculate Rx, Ry, take the square of Rx, square of Ry, take the square root, I get the magnitude of R. And then to find theta, this angle theta, all I have to do is to take Ry divided by Rx and then find the tangent of theta. And then I can just take theta and invert it in this manner. And that will give me the resultant magnitude and direction. So that's another way that you can have solved example 1 and 2. I encourage you to actually use this method. This is a method that will be used, and that's the one I want you to use. Example 3, all these examples go on and on and on, and they all work very similarly. So I have vector f1, vector f2, vector f3, vector f4. What I want to do is determine what vector f1 is along the x and y direction. And you can project it. F1 can be projected into the x-axis by taking the f1 of cosine 30 to get that one there. You can get f1 projected into y-axis by taking the cosine of the complementary of the angle, so that's cosine 60. And so you get 150 times the cosine 60. So you can now take each of these vectors, put them along the x and y axis by projecting them, do the same for F2, F3, F4. If I want to determine the resultant force in bolt A, you can do it very quickly by adding all the forces along X, all the forces along Y, and then calculate the magnitude and direction. Here's the example. So if I can take it, I can go ahead and do that. And I've shown you already how I did it for F1. F1 is cosine 30. This is F1 of cosine 60, which is the same as F1 sine 30. And so I will just do it for F2, F3, F4. You can create a table of the X components for F1, F2, F3, F4, for the Y components of F1, F2, F3, F4. You know their magnitudes. You can create a table, add them all up, all in the Fx direction, all in the Fy direction. That gives you a resultant of Rx and Ry. You can see the Rx direction is the Rx component is much larger. So, but that vector is going to look like this. This is R vector with a very small component of y of 14.3, with a large component of x of 199.1. And so as a consequence, I can now take the magnitude of r, so rx squared plus ry squared square root gives me the magnitude of r. The tangent of alpha is a ratio of 14.3 divided by 199.1, and I can now calculate that angle. So in other words, given a set of concurrent forces, I'm able to decompose and project each of these forces into X and Y, add them all up to get the resultant force to determine which way is the effect. Basically, all these forces are acting in different directions, but there's a single resultant force that if you were to apply that and replace that force, instead of having all these four forces, if I replace it with a single resultant force, which is now acting in this manner, is going to give me it's going to give me the same result as if I had these four forces acting to that point A. So that's a benefit of this, because you can now simplify a lot of different problems using this method. Here's another example, a little more complex. You have a tension in a gay wire of 2,500 pounds, okay? Newtons, I'm sorry, 2,500 newtons. And the force components, we want to find Fx, Fy, Fz of the force acting on bolt A. We want to find the forces acting here, okay? So that's the question there. We know the tension along this guy wire, okay, of 2,500 newtons. We want to find the angle of theta x, theta y, theta z, defining the direction of this gay wire. So what is the solution? Based on the relative locations of A and B, because I have the coordinates of everything, I can determine the unit vector that points from A to B. That's easy. I know these coordinates, and I can then find that unit vector. And since I can find those unit vectors, I can calculate the corresponding angles very quickly. Theta x, theta y, theta z. It's a geometry problem purely. So I can now arbitrarily put a coordinate here, and just using simple geometry, if I subtract the coordinates of this point to the coordinates of this point, I'll find the vector that points from this to that one, and you will find it's 40 meters times I hat plus 80 meters J hat plus 30 meters K hat. So the magnitude is 94.3. I'll now take the AB vector and divide that by 94.3 to get a unit vector. You have to do that to get a unit vector. And now to determine the components of that force along the three directions in the X, Y, and Z, I know the magnitude is 2,500 newtons because it was provided to you in the problem statement right here. And so I'll just go ahead and multiply 2,500 times this unit vector to get the components of that force along the three different axes. And this is the result of that. I can also determine the direction coordinates of that vector. I know these values from the previous problem, so I can find theta x, theta y, and theta z, okay, which is provided by these angles that you see here. So that concludes example 4, and I'll go to example 5 now. So example 5 is another problem, and they all are about the same. So I have a screw eye, it's subjected to two forces, F1 and F2, and I want to determine the magnitude and direction of the resultant force. If this is 15 degrees, that's 10 degrees. I can determine that either by projecting F1 into X and Y, F2 into X and Y, and then add them up and just find R, and then basically find the angle in that manner. And that's the way I recommend that you do it over and over and over. Or you can do it graphically, which is another approach to do this problem. You can basically draw a line here, draw a line here, make it parallel to that one, make it parallel to that one, and then just graphically draw a line from here to here, and that's your resultant vector. That's your force F, which if I were to remove these two vectors, these two forces, and just apply a force F that replaces that, that'll be an equivalent way of representing the problem. I'm not going to go into extensive detail because this is a purely geometric problem. You can draw it by hand and figure it out. So there are several ways to approach it. You can use the parallelogram approach that we talked about earlier. You can use the law of sines like I discussed earlier, and basically solve the problem as I did before. Here we use the law of cosines as an example. So I know this vector, I can translate this vector I can translate this vector f2 to this side here. And so that's what I've drawn here in figure 211. And so once you have that, I know this angle. I can determine that angle geometrically. So use the law of cosines simply to find the magnitude of FR. And I get 213 because I know the magnitude of F1 and F2. I know the angle in between them, so that's a quick calculation. I can also then apply the law of cosine, the sines, to find the angle theta that goes from here to here. And since I know this is 15 degrees, I can then find the total angle theta, which basically gives you 39.8. So I have 39.8 plus 15, I get 54.8. So, that's two approaches. The third approach will be basically use projecting each of those forces, F1 and F2, into the X and Y axis and follow the process that we talked about. So there's yet another example 6, resolve the horizontal 600-pound force into the components along the U and V axis. U axis is this one, V axis is this one. And then we want to determine the magnitude of those components. So if this is 600 pounds, and I want to find the components along U and V, I can draw this one right here. I can draw a vector F, which I don't know what it is. I can draw this vector F, which I don't know what it is, and figure out basically the approach to solving this problem. And so in this problem, we can do that. It's all a geometric problem. These 30 degrees is 120 degrees. I can figure all that out. It has to be 120 because if these 30 and 30, that's 60, and this has to add up to 180. So I know this is 120 right here. So in essence, I can again draw this vector. I can move it to this side here. So move this vector down here, and that will force me into knowing, well, this 30 is 120, so this must be 30 degrees. And so now the problem resolves into these 600 pounds, and you can quickly now solve it using the sign, this law of sines. I know all these angles. I know this 600 pounds. This one is 600 pounds. So it's an easy calculation if you can be found to be 1,039 pounds, and if it can be found to be 600 pounds, because well, this is sine of 30, and this is sine of 30, and so that's an isosceles triangle. So that has to be 600 pounds. So that's a quick way of doing it. Very simple process. I hope that's a clear example of how to apply it very quickly. So you can also determine in another example 7, if I have two forces, 200 pounds, and another force F in this direction. Well, I want to determine the magnitude of the component force F and the magnitude of the resultant force FR if FR is directed along the positive axis Y. So if FR is directed in this direction, I know this 200 pounds. What is F to make F the resultant to be along that? Like how to force that to be in that direction? Because if I have two forces applied, there has to be a force F such that the magnitude of F such that FR is always pointed upwards. So that's the question here. So I know this is 200 pounds. I can draw that geometrically. I know this 45 degrees. I know FR is always pointed upwards. I don't know what F is, but geometrically I'm kind of forced because I know the distance, this distance. I know this is pointed upwards. So this 200 pounds, this is 60. That's 45 degrees per this problem statement, because I can move F, so it's drawn here. And so I have a triangle now. These 45, 75, 60. And now I'm forced, and I can use the law of sines again to solve the problem, because I know sine of 75, sine of 45, sine of 60. I know sine of 45 divided by 200, sine of 75 divided by FR. So That's exactly what I've done here, and I can calculate the magnitude of FR and the magnitude of F using the law of sines. In this example 8, again, this continues to be very similar, the way you approach each of the problems. If I want to determine the X and Y components of F1 and F2 acting on the boom in this figure, so this is a boom, this kind of boom shows up everywhere, spacecraft, a lot of different applications. I want to express each of the forces in the Cartesian vector. So if I have the force F1, all I have to do is project that along y and x. So that's 200 newtons times the cosine of 30 to project into y, 200 newtons times the cosine of 60 to project it onto the x-axis here, and that will be acting in a negative direction. That's exactly what's shown here. You'll see that F1x is negative of 200 sine of 30, which is the same as cosine of 60, and you get minus 100 newtons, which is pointed in the left direction. And then the force can now be projected into y direction to get that component, and you get 200 cosine 30, which is 173 newtons. The F2 can also be resolved very quickly using the same approach as we have discussed. But here they're giving you slopes. As long as you find these angles, you can follow the same process. If you can find this angle, then you can then follow the same process we discussed earlier. So this is just a long way of doing it. You can just find these angles using geometry, and then use F2 times the cosine of this angle to project into X, and then F2 project into the Y-axis to get the vectors F2X and F2Y. How that force is representing the X and Y-axis, okay? And so now that's what they've done. And so in Cartesian notation, you can also write those vectors very quickly. Example 9 is looking at, hey, how if I know force F1 and F2, can I get the resultant force using the approach I discussed, which is adding the forces in the x direction, adding the forces in the y direction, once you have represented F1 into x and y, and once you have represented F2 into x and y. So the first step is to determine F1 into the x and y axis, F2 into the x and y axis, and then add them up, the x's first and the y second, and then create your resultant force. So that's fairly simple. I have 600 times the cosine of 30 to project it into the x-axis. That's that one. Minus, then I have this one here, F2 project into the x-axis is 400 times the cosine of sine of 45. So that's this one right here. And so you add them up and you get 236.8 newtons. You can then do the same process in the y direction. 600, this force vector here, times the cosine of 60 projects it back into the y-axis, or you can also, cosine of 60 is the same as sine of 30, so you get that, plus, and now this force vector, again, gets projected to the y-axis, that's 400 cosine 45, you get 582 newtons. So these are the two components of the resultant force Fr, and so now you can find the magnitude of Fr, which is each of these square root, that gives you the magnitude. And from the vector addition, you get the theta, divide this by that to get the angle. And so that gives you the resultant force Fr, which is shown here. That's your resultant force Fr. And so that is a way to approach it. And you can also, take each force and express it as Cartesian coordinates in this manner, Cartesian vector I meant, add them up, and then you get F1 plus F2, which is the same thing we discussed before, graphical solution. And so once you add them up, this is your resultant vector Fr, and then you can find the magnitude using the same formula and the angle given here at the bottom. So what he's trying to accomplish here is that given a set of forces, what is the magnitude Fr given the set of forces? That's a question that's being asked, and which direction is it pointed to? Very useful application in statics. Problem number 10 is another one, it's saying, hey, if this magnitude here is 200, express that force F in the Cartesian vector. So again, project F along each of these axis. So F cosine 60, F cosine 45 gives you in the Z direction, and then F cosine alpha gives you in the X direction. That's the approach to do this. But you know that cosine of alpha squared plus cosine of 45 degrees plus cosine of 60 degrees, square each of those, that should give you 1. So you can calculate alpha very quickly. And so if you know that, you can now find the force vector F as simple as F cosine alpha plus F cosine beta plus F cosine gamma. And so you know the alpha, beta, and gamma, because it's given to you in this problem. So you can then determine the force vector F in each of these X and Y, Z directions. The magnitude is 200 newtons. You can determine that by taking 100 squared plus 100 squared plus 141 squared and doing the square root of that, and you will get a 200 newtons very quickly. So I hope this example is clear. We'll go to example 11. They're all very similar. If I want to determine the magnitude and coordinate direction angles of the resultant force acting on the ring for a vector given F1 and F2, just add the I. This one does not have any components of I. This one has it, so that's 50 right there. And then you have 100 in the Y direction minus 100. You have 60 for vector F1 in the Y direction. So that's 60 minus 100. That's 40 minus 40. And then you have 100 pounds acting in the Z direction for vector F2, and 80 in the Z direction. That's 180 right there. So that's your resultant force, 50 minus 40 plus 180. These are the components in each of the X, Y, and Z directions. The magnitude is just simply 50 squared, 40 squared, 180 squared, add them up, square root, 181 pounds. So that gives you the magnitude of that force. It's not very difficult to find the angles if you know how these vectors are oriented. Like I know how this vector is oriented, so I should be able to tell you how this force vector is oriented in the 3 axes. Okay, you can find those angles very quickly. We discussed that earlier. I have this vector F. Just simply divide that by its magnitude, and so that'll give me a unit vector. Okay, so take that vector divided by the magnitude, that'll give me a unit vector. And each of these coefficients, if I find the inverse of the cosine, gives me the angles relative to the X, Y, and Z axis. Okay, and those angles are shown here. The alpha from this resultant F to the X axis, the resultant to the Y axis, and the resultant to the Z axis. Okay. And so I can now move to example 12. They're again very similar problems. If I have vector F of 100 pounds, and I know what the angle is to this plane given by X and Y, and then I know the angle to the X-axis of 45, that's simply taking this vector F and projecting to Z, and then projecting it into this plane, and then projecting into Y, and then projecting to X. So a very, very simple process. If I want to find out how F is projected to Z, I have to find this angle. Well, if this angle is 60, I hope you know this angle is 30. So all I have to do is take F, 100 pounds, cosine of 30 to get it into the Z direction. So that's 100. Cosine of 30, which is sine of 60, is 86.6 pounds. And then I take this vector and project it downwards into this plane. So let's call this F prime, the one that gets projected here. And that will be, sorry about that, that will be F cosine 60. So I project this F onto this plane. The vector here will be F cosine 60. That's 50 pounds. Now I take that vector and project into Y and project into X. Well, that'll be F cosine 45 for the X direction and F sine of 45 into the Y direction. That'll give me 35.4 pounds each. So now I know that F has these components, and you can show that magnitude gives you exactly what we got in the problem statement, which was 100 pounds. And how do I know that? 35.4 squared plus 35.4 squared plus 80.6 squared. Square root of that will give you 100. And so that clearly shows you how that's worked out. I can now find the angles of f relative to the x, y, and z directly. If I want to find the angle between this vector f relative to x and so forth, all I have to find is a unit vector. So I know the components of f, which are this, divide that by 100, and that'll give me a unit vector u. Once I have that, this represents the direction cosines, and I can calculate the inverse of those cosines, these values here, and then I get the alpha, beta, and gamma, which represent how this vector is oriented relative to x, y, and z. Example 13 yet is another variation of the problem. Again, all these problems are very similar in nature. Here, I gave you the angle of f relative to x, y, and z. So that's way easier. Now I have 300 newtons. Cosine of this gives me the fx direction because I'm projecting f onto x. So that's f cosine 45. That's this value here. Then this one is projected into that one. So that's cosine 60. And then f projected to z, that's cosine of 120. So now I know the components of the vector f1. And the question here is, uh, can you find the magnitude of f2? So what is the magnitude of f2 here? Uh, um, and the direction angles of f2 such that the resultant force fr acts along the y-axis. So if I have a force F1 acting on this hook, there must be a vector F2 such that the resultant force acting on this hook along the y-axis has a magnitude of 800 newtons. There must be a way. So I know F1, I know Fr basically, because I know Fr is acting to the right. So that's 800 newtons times J hat. So all I have to do, I know that F1 plus F2 is Fr, because Fr is a resultant of F1 and F2. So I have to do is add F1 and F2. I don't know the components of F2, but that's fine. I just add them up. I know 800 J hat, so uh, I know that 800 must be equal to this here. Uh, this one, Fr has no I hat, so this is equal to 0 right there. And then on the left-hand side, I don't have K hat, so this must be 0 as well, this coefficient. And so I can solve for f. So for example, in the first case, this coefficient is 0. So I can solve for f2x. I can solve for f2y. You're looking at this is equal to 800. And so I can then solve for f2z by making this equal to 0, since k hat does not show up in the left-hand side. And so now I have the components of f2 that make that happen. Once I have that, I can find the magnitude of that by taking the square root of the coefficients of these forces. Square root of that, that's 700 newtons. Take this vector that we found, the components of this vector, divided by 700 newtons gives me the angles. I can calculate the angles from there. And the results are shown here. Okay, so the last example I have is simply now I have the coordinates for a rubber band that attaches point A and B. I want to find the length and direction from A to B. So that's simple. I know the coordinates of this point, the coordinates of this point. If you know the coordinates, you can find out R hat. So you basically want to establish a position vector going from A to B. And so I encourage you to, one approach is to make one of the coordinates 0, 0, 0. But you don't have to. The coordinates here is 0, 0, 0. So you can find the coordinates of this point, find the coordinates of this point, subtract the coordinates in the x direction, the y direction, and z direction to find the vector that points from A to B. Okay. And so if I'm pointing from A to B, subtract the coordinates from this one, start with this one, subtract this one. Okay. And then you can find a unit vector very quickly by taking the 7 meters and taking r hat divided by 7 meters. That'll give you the unit vector you're looking for. And then you can find the angles using the direction cosines. We have many more examples. So let me hit example 15. here. Example 15 is a man that's pulling on this wire, this cord, with a force of 70 pounds. We want to represent that force acting on support A as a Cartesian vector to determine its direction. And so the first step is to figure out the vector that connects A and B. Okay. Um, again, put some coordinates. You know that the origin is 0, 0, 0. So you can figure out the coordinates of this point, the coordinates of this point, and just use geometry to determine the position vector R. And that's found to be 12 hat minus 8 hat minus 24 k hat. The magnitude of R can be found as just taking the square of 12 squared plus 8 squared plus 24 squared, square root of that, that's 28. And so you can find a unit vector by taking the vector here divided by 28, and that will give you the unit vector. Once I have the unit vector that points along this line here, I can now multiply 70 times this unit vector to figure out the components of the force F along each of the X, Y, and Z axis. So that'll give me 30I minus 20J minus 60K. You can then now use the direction cosines from the unit vector 12 over 28, 8 over 28, 24 over 28 to determine how that force is directed. Because we figured out the magnitude, we can also figure out how it's oriented relative to the X, Y, and Z axis. Example 16 is a quick question here of the roof being supported. It's supported by, you have this hook that's supported by these ropes, A, B, and AC. You have a force of 100 newtons this way, 120 newtons this way, that's applied to that hook. And the question is determine the resultant force acting on hook A. It's the same process. Again, you want to determine your origin, then find these coordinates, and these coordinates. Find the vector that goes from point A to point B, point A to point C. Again, that's pure geometry. You can determine that unit vector to be this one right here. So multiply by 100 newtons, because I know what that is, gives me the force F in the X, Y, and Z axis. Here, this represents the I component, which is the X component of that force in the X direction. And then it doesn't give you anything actually in the Y direction, but gives you something in the K direction, which is the Z direction, okay? And so I have the vector force that's directed from A to B. I can now find the position vector from A to C using analytical geometry again. The position vector, that's pure geometry. And so again, you can find, 120 is the force from A to C. So take that position vector, that's a unit vector now, because I have the position vector divided by 6 gives me a unit vector. So that gives me a force F of 80 plus 40 plus minus 80K hat. And so I know that I have 80 in the X direction, 40 in the J direction, and 80 in the Z direction. So I now can add the two vectors FAB, so this vector FAB and FAC, by simply adding the components of I, which is 70 plus 80, that's 150. I don't have any J here, so this J stays alone, and then I have K, which is 70 plus 80, that's 150. So this is my resultant force FR. Again, that's a resultant force FR. Like if I didn't have these two vectors, if I apply FR, I have the same system. I have a force applied in that direction is equivalent to these two forces. Now with this information, I can find the direction cosines again, and I already shown you how to do that. Example 17 is to determine the magnitudes of the projection of the force F, this force F, onto the U and V axis. So that's simply 100 newtons times cosine 15, and then 100 newtons times cosine 45. So it's a very simple problem, how to project a vector of 100 newtons onto two axes. Example 18 is perhaps a little bit more complex, but not that hard. I have a frame, a complex frame. It's subject to a horizontal force of 300 newtons, and I want to determine the magnitude of the components of this force parallel and perpendicular to the member AB. So I want to know how that, how that force is, along AB, like what's going on there. And so that's the question. It's very useful to draw it. So this force F, I want to know what is FAB and perpendicular to it. That's really what I want. The strategy is going to be to find this vector, the one that connects A to B, find the unit vector along that, and perhaps I can go somewhere from there. So the magnitude of the component of F along AB is equal to the dot product F and the unit vector UB. And that will define the direction AB. I know, because if I know the coordinates of this point, 0, 0, 0, I can figure out the coordinates of this point, okay? That's not very hard to figure out what the coordinates of that point are. And so then I can find the vector, which is basically 2i plus 6j, 3k. You can figure it out quickly. 6 in the y-axis. This point is like about 2 in the x-axis, and then a height of 3. So that's where these 2 and 6 and 3 come from. I can determine now the magnitude, and if I take this ratio, I get a unit vector. Okay. So now that I have that, it's easy now to take this force F, okay, this force F, and project it along this line. And so that's simply F dot UB, which is F cosine theta. And so I know F, which is 300J. And so all I have to do is take that dot product, and I get 257.1 newtons. And that's a force acting in that direction. Sorry about that. And so you can now express this vector Cartesian, that vector. If I know it's 257.1, I can multiply that by UB, which is along the line AB, to figure out the components of this force along the I, J, and K directions. And so that's exactly what was done here. 257 times each of these components gives me these components. The perpendicular component has to be by just looking at a diagram, because if I know this vector F and I know this vector F, this vector that's perpendicular is just graphically this one. So by using the law of triangles, I know F, which is 300. I know FAB, which is this one here. So I can definitely find F perpendicular to be this one. And then you can now calculate the magnitude very quickly. You already know the direction. You can calculate the magnitude, which is 73 squared, 80 squared, 110 squared, square root of that. That'll give you the answer that you're looking for. Example 19 is a pipe that's subjected to the force of 80 pounds. And that force of 80 pounds is given to be in this direction. The question there is to determine the angle theta between F, this force F, and the pipe segment AB, and the projection of F along that segment. So again, it's a similar process as we've done before. You have to find the strategy, general strategy is to find how these pipes are oriented using vector notation. Okay. The first step is to find the vector, position vector BC, the one that connects B to C, and then to find the vector that connects B to A. And again, that can be done by just simply following, I gave you the coordinates. We know the origin is here. So if I know how each of these points are located, I can then figure out the position vector. And once I have those position vectors, I can find their unit vectors. In this case, I know this vector, how it's oriented. I know this vector, how it's oriented. I can now use the dot product of these two vectors divided by their magnitudes will give me the angle in between. That was the formula for cosine and theta of two vectors. And so that will give you a 42.5 degree angle. And now I know 42.5-degree angle. Now I can take F and then project along FBA by just simply taking 80 times the cosine of that angle, and then this force times the cosine of the complementary of the angle. That's one approach, and that's what was done here at the bottom. Here is shown a different way of doing it. You have the force vector F, you know their components of that vector. Take the dot product against UBA, and that will give you that component of that force projected along AB. And so now you know the force along AB due to this force applied of 80 pounds. So I hope that these examples were useful in demonstrating the concepts that we're trying